Welcome everyone. This is the Internet Ecosystem and Evolution lecture series, and this is the second installment of our lecture series that is about Internet routing and the large-scale structure of the Internet. In the previous lecture, we introduced what we call the AS level architecture of the Internet. Recall that the AS, an autonomous system, is this collective name of all the different organizations and organizational networks that make up the Internet. When we describe the Internet as an internetwork of autonomously operated networks, so basically these autonomous systems, which are in themselves, can be pretty much non-trivial topologies in themselves. They connect their networks into some internetwork, which we call the Internet, and then we describe this architecture at a very high level view. We try to find a model to describe this process when two autonomous systems decide to connect their networks with an AS-AS link, which is basically just a connection between two autonomous system border routers of our autonomous systems, and we try to find a description or a model that gives us a good idea on when it is the case that two ASs decide to establish such a direct link between their ASs. And in this particular lecture, we're going to just see how this very simple service model just transforms into AS level routes or routing protocol decisions out there in the Internet. Recall that this service model consisted of two very simple types of business relationships that we said may exist between two autonomous systems. The transit relationship, when one autonomous system buys wholesale internet access from the other autonomous system, and the peer model or the peer relationship, whereby two autonomous systems decide to just exchange their and their customers' traffic for free in order to save on transit fees. So this was basically our service model, and then we also described this high-level architectural view of the Internet that we call the transit hierarchy, which is basically just a collection of all these ideas into a layered model for the Internet large-scale architecture, where at the top of the topology there were these tier 1 autonomous systems, which were the largest service providers in the Internet, and then at lower and lower levels we see less and less let's say just important or smaller autonomous systems until we reach the bottom layer of this transit hierarchy with the stub autonomous systems, which just hang on as leaf nodes on this transit hierarchy. So this gave us a very good idea of how the Internet topology looks like from an architectural point of view. And this particular lecture will be about the second important topic that we are going to just derive from the service model, and this is the types of routes or the types of autonomous system level passes, forwarding passes that emerge on top of this architecture. But before being able to decide or talk about routing and routing decisions in depth, we'll need to just fix a couple of very basic definitions with respect to the basics of network routing. So we in the first part of this lecture series, we're going to discuss distributed and centralized models for Internet routing, static and dynamic routing, link state and path vector routing protocols. And we are going to make another distinction between intra-domain and inter-domain routing protocols. We've already described this distinction in the previous lecture, but we are going to just restate it here because this is a very important distinction in the internet routing system. And the second part of this lecture will be about mapping the service model to actual autonomous system level passes. So we are going to just describe, given this and this and this network topology, when this and this and this links are transit links and those other links are peer links, how these this simple or which kind of routes these particular autonomous systems will establish between themselves on this architectural view of our little internetwork. We are going to describe what we will call the very free routing model, which will be a very simple model of feasible and forbidden passes, which will describe the types of passes that are at least available for actual routers to use in this model. And then at the end, we are going to just refine this very basic, very free routing model with more sophisticated and more finely grained routing policies, in particular the preferred customer policy and the shortest ASPS routing policy, which will give us a very good overview of the policy routing system of the internet. But first, let's see some basics with respect to routing. First, we have to just fix a very important notion related to terminology, because in the internet and in the literature and discussions related to internet routing, the verb or the noun routing very often raises or causes misunderstandings, because it is used for multiple meanings. So in the rest of the lecture, we're going to just try to stick to a very important terminological distinction. When we are going to talk about the very process of that internet routers does, which is related to passing received packets from one port to the other towards the next IP address by longest prefix matching the packet's destination IP address in the forwarding information base, we are going to use the term forwarding to describe this this process, because this is actually related to forwarding actual packets in the data plane of IP routers, even though fairly often this process is also sometimes described with the term routing. Instead, we are going to just use the term routing to describe the process of setting up the forwarding information bases, or the FIBs of the individual routers that make up the network based on some control plane mechanism that the routers will use to exchange topology description information between each other, and based on so routing will be the process to actually build the forwarding tables or the FIBs that the forwarding process of IP routers will use to pass packets between the respective ports. Usually routing is a control plane process, and this is the responsibility of dedicated routing protocols, and this typically runs in software, while forwarding is typically a hardware-based functionality, and it is described in and this is implemented in the data plane of IP routers. And even though these two processes are often both called routing, we are going to just try to make the distinction of using the data plane functionality of traffic forwarding and the control plane functionality as routing. So clear, with these terminological problems clarified, let's just try to give a classification of the different types of routing mechanisms. So not forwarding, routing processes or routing functionalities that may exist in the internet. The first is the distinction between static and dynamic routing. Static routing actually means the process of a network operator to configure IP routers and the forwarding information bases or the forwarding tables of IP routers manually, usually just going to the actual site, connect a laptop to the actual router and a serial cable, or remotely through SSH, and using the command line interface to manually add forwarding information based entries to the router's data plane. This is a very simple process, and this allows the operator to basically describe any sorts of routing decisions. Problem is that this does not really scale. Of course, manual labor is the most expensive part of network operations, so doing this manually will of course not scale economically. Maybe the major problem is that this method does not adapt to topology changes. So whenever there is a link failure in the network, the operator would need to go out and reconfigure all the routers in the network to route around the failure. This is not an adaptive scheme. So this is only usable in smaller networks, and this is quite rarely used even in that case. Of course, the more dynamic process is to automate this manual process, and this is called dynamic routing. In this particular case, the forwarding information bases are maintained by a dedicated routing protocol, which is basically just a software process that runs in the control CPU of the router and uses some mechanism to update compute to forwarding information base entries and then download these into the data plane. Of course, dynamic routing can be adaptive and scalable, because this is something that routers basically do completely automatically. There are two types of two approaches to dynamic routing. In centralized routing, there is a dedicated route server that is responsible for all the routing functionality of the network. So this is also called a PC or PES computation element, or in software-defined networking, this is called the SDN controller. So this is basically just a central server that runs a sophisticated process which will compute forwarding information base to each and every router that is operated within an autonomous system, for instance, or within a network domain, and then just use the network to download these FIPS to the individual routers. So all routing functionality is basically centralized at a single point. Distributed routing is the opposite approach. In this case, each router runs a separate instance of the routing protocol daemon, and these routing protocol daemon will be responsible to compute the FIB of just that particular router locally, and in this case these routing protocol daemons will exchange routing descriptors, somehow learn routing information from the network autonomously, and then will compute and maintain the FIBs locally. There are two approaches to doing distributed routing. In link state routing, the routers maintain a distributed link state database that describes the entire graph of the network. So it's basically just what the mathematical notion of a graph is: nodes, which represent routers or hosts, and links between them, which of course represent link layer connection between individual routers. And then we can use a standard shortest path algorithm, like for instance Dijkstra's shortest path algorithm, to actually compute the next hops, and from that the fib entries based on the first hop along the shortest passes. Another approach is the path vector protocol. In this case, the routers are not aware of the entire graph of the network, because instead of basically just learning the graph itself, the routers merely distribute the available passes between each other. So whenever a router knows a pass, it just passes that information on to its neighbor, and then all the information that the router has from the network is the set of traversable passes instead of the entire graph. And in path vector routing protocols, each router can autonomously decide to pick a path that it considers somehow the best, and what it means for a path to be a best path will be a central topic in the rest of this talk. According to its autonomous local policy, and this permits very highly flexible policy routing. So these are the two major ways to run a distributed routing protocol. There's a third way, the distance vector paradigm, but this is becoming obsolete these days. So this is our taxonomy. Routing the main distinction between static and dynamic routing. In static routing, the operator configures manually and the routing table entries, while in dynamic routing, there is a routing protocol which does this, this automates this process. In centralized routing, this routing protocol functionality is realized or implemented at a central server, while in distributed routing, each router autonomously and runs its own routing protocol daemon instance and will somehow use a distributed process to build the FIBs at the routers. And distributed routing itself has two very important types: link state routing and path vector routing. There is another way to distinguish routing protocols and dynamic routing functionality, and this is somehow orthogonal to the previous classification, where in the internet we are talking about a two-level routing system where there are different routing protocols deployed at different levels of the internet architecture. We've already talked about it a little bit earlier, but let's just restate this distinction here. The intra-domain routing typically runs inside an autonomous system and decides on the routes between the hosts and the routers that make up a single autonomous system. The collective name for this routing protocol is the Interior Gateway Protocol family of protocols, so IGPs. And these IGPs typically implement a homogeneous routing policy, like for instance shortest path routing across a single AS, and are typically using link state routing protocols. In contrast to intra-domain routing, which runs inside an AS, inter-domain routing runs between ASs. So this is basically the routing protocol that is responsible for setting up the succession of ASs, or determining or computing the succession of ASs that one AS will use to reach some other remote AS in the internet. So this is basically routing between autonomous systems. The collective name here is Exterior Gateway Protocols, but there is only just one EGP that we are going to describe in the next lecture, and this is BGP. BGP is a routing or a policy routing protocol which allows us to basically every operator and the autonomous system in the internet to deploy its own routing policies by configuring their BGP routing protocol instances. And BGP typically is a path vector routing protocol, so it does not build link state databases. It only just uses the set of available passes to describe and set up FIBs. This is the big four, or the four important routing protocols that are now in use in the internet. IGPs, so the intra-domain routing protocols, are typical link state routing protocols, like OSPF is the open shortest path first, and IS2IS is the intermediate system to intermediate system routing protocol. And at the top, or from a high level view, these routing protocols are very similar to each other, so both are link state protocols, but a closer look will reveal lots of small differences between these routing protocols. We are not going to detail these routing protocols here. We assume that in your former studies you already got familiar with OSPF and IS2IS. There is also RIP, the Routing Information Protocol, which is an old routing distance vector routing protocol that is now in less and less use. So this is basically the IGP landscape. There is also ERGRP, which is Cisco's proprietary routing protocol, which is also in heavy use out there in the internet. We are going to just not deal with this here. Our interest is EGPs, and basically the BGP routing protocol that runs between the ASs, and this is a path vector routing protocol that will be the main topic for our next two lectures. We have to, before just closing this part on the basics of internet routing, we have to unfortunately discuss a very nasty and very confusing part of internet routing, and this is the collaboration of the intra-domain and the inter-domain routing protocols out there in the internet, because there are lots of confusions and lots of configuration errors emerge and originate from this highly complex way different routing protocols can interact in the internet, and the reason for this is that this nice distinction between intra-domain and inter-domain routing protocols is not that nice in practice. In reality, in fact, there is a very complex interaction that may go between EGPs and IGPs, and this can often cause problems. So here's the problem. In short, there are lots of routers out there in the internet, and this is typically the autonomous system border routers, which are used by an autonomous system to form these relationships with the rest of the internet and the rest of the ASs that need to run multiple routing protocols. So for instance, here, this particular router, it needs to run BGP, so it's like an EGP, to exchange routing information with the border router of AS2, but it also needs to run an IGP to exchange routing information with all the rest of the routers that make up this autonomous system, to be able to learn the routes that exist within its own autonomous system between different routers. So what happens here is that this particular router, for instance, here runs an IGP, which, recall, is responsible for learning routing information and distribute routing information within an autonomous system, and it also runs an EGP instance, which it uses to exchange routing information with neighboring autonomous systems. And we are going to just see in a minute that this particular setup may lead to very unfortunate situations and lots of confusions on how to actually interact, how these routing protocol instances interact via this process, which is called the fib manager. And even this is not a complete picture of what's going on there, because there is also a third constituent of the whole picture, and this is the IBGP protocol instance. But in order to understand what IBGP actually does, let's just take a very simple example. In this particular example, we are operating AS3. AS3 has two neighboring autonomous systems. Let's just maybe assume that this is two transit relationships to AS1 and another transit relationship to AS2. So AS3 actually multi-homes to these two provider ASs, and it learns routing information from these autonomous systems. For instance, in this little setup, we have AS2 that announces the IP prefix 10.1.1.0/24 to the rest of this little internet, which, recall, essentially means that it generates a BGP message from its border router to the rest of the border routers in this little internet, which tells these other autonomous systems if they have a packet whose destination address falls into this or belongs to this IP prefix, then they can essentially use AS2 to actually reach the hosts that are numbered, that have IP addresses assigned from this IP prefix. So this is basically just an announcement which will tell R2 and R4 that IP prefix 10.1.1.0/24 is actually located in AS2. In this particular setup, R4 forwards this announcement to R1. So actually, our actual autonomous system will learn two passes to this remote autonomous system. At R1, it has a pass through R4. This is a two-hop AS pass, and at R2 there is another pass, which is a single-hop autonomous system path. Now here's the problem. So far so good. What's the problematic here is that imagine that the situation is the following. Suppose that the primary provider is AS2, which basically means that AS3 will want to route all traffic to the internet through AS2 because, for instance, the transit fees that it can negotiate with AS2 are much lower than the transit fees it can negotiate with AS1. So it will by default it will want to use the path learned through R2, which is a direct path to AS2 instead of this other path that it learns through R1 because this is the cheaper path. And we'll only just want to use the secondary path whenever the primary path, for instance, fails. How to actually just but recall the problem is that the information that there is a direct path between AS3 and AS2 is only available at R2 because there is no mechanism to distribute the announcements of AS2 within this autonomous system. Now this is the actual responsibility of our third constituent, our third routing protocol, which is IBGP in this particular example. IBGP is a third routing protocol, which is often called the internal BGP. This is a version of BGP which is run inside an autonomous system to exchange routing information learned from other external autonomous systems within an autonomous system. So here's the deal. R1 learns a route from eBGP, which we're going to just use the name external BGP to distinguish BGP when it runs between autonomous systems. So R1 will learn a routing announcement for this remote IP prefix from R4 via eBGP, and it will also run an IBGP instance and will learn routing information through R2 to this IP prefix. So it will have when we actually just deploy IBGP alongside the OSPF and eBGP in this particular case, then R1 will have complete information about the availability of the autonomous system level passes in this little setup, and then it will be able to deploy its own policy and maybe use this particular path to reach the IP prefix instead of this one, which will, as we just assumed, will be, for instance, cheaper for AS3 instead of using the secondary path. Of course, this setup is much more difficult than what we could describe here and what we could discuss in more depth. Instead, in fact, we could dedicate a separate semester to just deal with the complexities that may arise through the interaction of the eBGP, IBGP, and OSPF. Next year, there will be a lab which will be about the most important problems of such integrated routing or heterogeneous routing architectures. The only thing, the takeaway that you must recall or remember is that the interaction between the external exterior gateway protocols and the interior gateway protocols, so that the interface between intra-domain and inter-domain routing can be highly complex, and there are lots of complexities involved in making sure that the autonomous system level routing policies of multi-homed ASs are consistent across all the autonomous systems, and next year we'll have more time to actually discuss the complexities related to this setup. We've seen that in this particular setup, we've already seen that a single router may run multiple routing protocol instances side by side. For instance, an eBGP, an IBGP, and an OSPF instance, and then it needs a dedicated mechanism to choose the IP prefixes or to actually just synthesize all the information that is available in the routing information bases or routing databases built by these distinct routing policies to synthesize all this information into a consistent fib and this is the responsibility of the so-called fib manager process, or the fib manager functionality that is implemented in routers. So it's basically just responsible for assembling the single forwarding information base from the individual routing information bases that are maintained by the different routing protocol instances. How this actually done? It's very simple. Operators associate administrative weights to each protocol, and then if a prefix occurs in more than one routing information base, then the smallest weighted routing protocols win. Okay, so for instance, when there is a remote AS or there is an IP prefix that is, for instance, we have a local route, so it is available through a direct interface, then no matter what the operator configures statically, no matter what we learn through OSPF, eBGP or IBGP, we will use the local route because it has the highest preference based on this setting. The second highest priority is a static route, so static routes that are put there and configured there by the operator override all possible routing protocol decisions that are learned through any of the routing protocol instances, like OSPF, eBGP, and IBGP. In this particular setup, OSPF overrides any BGP, and usually eBGP routes override IBGP routes, but this is just a default setup, and the operator is actually free to assign these weights to each protocol freely, and then just can decide which the priority between these different protocol instances. We're going to, for instance, just see, let's just very, very shortly describe what this means, this default priority order will mean in our little setup, because it has a very interesting consequence. Observe, for instance, here that R1, as we described, learns routing information or the availability of this remote IP prefix through two different routing protocol instances. It learns the 2-hop AS path from R2 via eBGP, and it learns the single AS hop path through IBGP. So there are two routing protocol instances that maintain reachability information with respect to this IP prefix. And in this particular case, the fib manager will need to decide. But since in this order, in this case, we've seen that eBGP is has higher priority than IBGP. Therefore, R1, by this default prioritization, will use the external route to the remote prefix instead of the internal one. So if the operator will want this to be the other way around, so use this particular path instead of this particular path, then they will need to override this priority and swap these two instances in the configure these priorities differently. This is called hot potato routing, and later on we are going to describe hot potato routing in a little bit more detail. Now it's only enough to learn that the fib manager is the actual process that is responsible for synthesizing the different routing information bases built by different routing protocol instances into a single, consistent, and well-behaving fib, and use this fib to download this into the forwarding functionality of the router, which will actually just use this fib to pass packets on between the different ports of the router.